Hello again everyone, welcome back to ptet.chemistry channel. So in this video, I'll cover specifically calculations involving equilibrium constant that's to do with Kc. This is the first part of two video series on Kc calculation. So any equilibrium constant, whether it's Kc or Kp, which I'll cover in another video, or any other equilibrium constant, the value can only change when temperature is changed. Okay, so when temperature is unchanged, Kc doesn't change. So we start off nice and easy there. With this example where they ask for expression on Kc. Note that all of these are equals, so we would take the concentration of a solid as unity. So otherwise, if we take it as 0, it will not make sense in terms of the Kc or Kp equation. Yeah, so for Kc, we take the concentration of solid to be just unity or just 1, in the sense that we do not include solid concentration in our Kc. Okay, if we do, then it's just unity value and it will not make a difference. So big K and small c, you gotta write it properly. Square bracket for concentration. Concentration of the product, this each species of the product. The product is I minus and Fe3 plus. The product is not 2I minus. Okay, the 2 refer to the mole ratio in the balance equation. And that is the power to which you must raise the concentration to in the Kc equation. Okay, so I got the 2 there because it's got 2I minus as a product on the right hand side. So it's I minus square bracket for concentration to the power of 2 multiplied by the other concentration of the product, also to the power of 2 because you got a 2 in front of the balanced stoichiometric equation. So Kc is to do with the product concentration divided by the reactant concentration. I include I2 there because it's I2 aqueous. If this is I2 solid, I wouldn't have included it in. It's to the power of 1 because without stating anything, it's just 1 there for it to balance out the equation. Yeah, so I have to include that. And then the Fe2 plus is just square. Alright, so that is just expression. What they like to ask sometimes is always get the units. Alright, so each of these refer to mole per dm cube because there's a standard unit for concentration. So that is square, and then this is mole per dm cube square as well. So I'm just following through from my expression, alright, which I could get correctly. But working out the units, sometimes people mess up. Okay, so I hope by writing them out like this, you can see that this is mole per dm cube square, mole per dm cube square. So this and these can cancel out. So what does that give you then? So you have 2 lots of it, you have 1 lot of it, so you can cross out that and that become 1. So the unit will cancel out to just mole per dm cube. Very simply just like that, even though it's not asked, but sometimes they do ask you in a theory paper. Okay, so in this example 2 is when we start talking about numerical value of Kc. So you're given an equilibrium here. This is aqueous, aqueous, aqueous. This is solid. So remember we talked about the concentration of solid having the concentration of just 1 being unity. So that's why its concentration does not appear in the Kc at all. What do we have? We are given mole, and the volume is dm 1.00 dm cube. So it's very important that we realize that mole is not the same as mole per dm cube. Okay, so concentration is in mole per dm cube. So yes, it's a bit lucky here that you have 1 dm cube because you could just use the mole and then it's divided by 1 dm cube. But you got to interpret it in terms of mole per dm cube anyway, because not every single time is going to be 1 dm cube. Alright, so if I write down the expression is the concentration of the product, which I already taken the concentration of the solid to be unity. So the concentration of Fe3 plus in the proper square bracket, not a round bracket, a square bracket for concentration, is to the power of 1 because in the balance equation here is just 1 there, divided by the Ag plus concentration to the power of 1 and the Fe2 plus concentration to the power of 1. So it's nice and simple there, but they want us the value. So the Fe3 plus, okay, it's not nice and simple here. It's actually slightly tricky. Okay, let me just move this aside. So it is saying that Ag plus Fe2 plus form Ag plus Fe3 plus. Okay, so they're saying that initially, so you need to start thinking about what has reacted and what is formed here. Initially, you have 1 mole of the silver nitrate. 1 mole of silver nitrate will give you 1 mole of Ag+. Because I hope you can see that AgNO3 giving you Ag+ is 1:1. Okay, so that is initial mole. The initial mole or FeSO4 is 1 mole as well. And of course, you get no product at start. Okay, mole at equilibrium. What are you given? There's 0.44 mole of Ag+ in the mixture, so 0.44 mole. So what I can say really is, you started from 1 mole, now you're left with 0.44. So how much has reacted? So the mole of Ag+ reacted. It's very important that you see exactly what is happening. Whatever that reacts will give you the product. The products are formed from whatever that has reacted, not what you're left with at equilibrium, but how much has reacted. That's very important, yeah? So it's going to be 1.0 minus 0.44. So that's 0.56 mole. Alright, and how you can see from the balance equation, 1 mole of Ag+ reacts with 1 mole of Fe2+. So the Fe2+ reacted is equal to the mole of the Ag+ reacted, which is 0.56 mole. If you started with 1 mole, then you reacted 0.56 mole, therefore you will also end up with 0.44 mole. And importantly also is that 1 mole of Ag+ reacts to form 1 mole of Fe3+. Okay, so I should probably add in a new page here so that I don't run out of space. Maybe I can move that. No, I'll leave it there. I'll move this down there. Okay, cool. So what do we know? We know that that is whatever that reacts, right? So whatever that reacts form whatever the product is. So the mole of Fe3+ formed is to the mole of Ag+ reacted. Okay, it's going to be 1:1. I'm just putting it into words and explaining it 1:1. In reality, you can see that that is very clear. The iron 3+ form is just going to be 0.56 mole, because that was how much of the Ag+ has reacted. Just from this information, how much is left at equilibrium means how much of it has reacted, which is 0.56, and I could get how much of Fe2+ has reacted, and therefore I could get how much of it is left at equilibrium. And I know 0.56 mole has reacted. From the mole ratio of the whatever they reacted, I can get whatever that is formed, because it's 1:1, I get that to be 0.56. Alright, so just putting it into the Kc equation then. Kc is just, I can just copy this really. So Kc is just whatever expression that I could write there. And then I can just put in the value, which is 0.56 mole over 1 dm cube. So that is mole per dm cube. Alright. And then the Ag+ is 0.5, hang on, it's going to be the concentration at equilibrium. You see, this is at equilibrium. This is concentration at equilibrium. So we need to be careful. The concentration at equilibrium is the mole at equilibrium divided by the volume at equilibrium. So it's 0.44 for each of Ag+ and Fe2+. So that's for Ag+. This is for Fe2+. It's to do with concentration at equilibrium. Yeah? So this is why a lot of students find this kind of calculation tricky, because they do not understand that whatever product you get comes from whatever reactants that is formed. Okay, so all this value were given was in, this was 3 sig fig, this was 2 sig fig, and 2 sig fig, and 2 sig fig. I would most likely put it to 2 sig fig simply because a lot of the data was in 2 sig fig. Actually, it has a unit as well. I know the question doesn't ask, but the top bit will be mole per dm cube. That's why I do not just write down mole. I write down mole per dm cube because there is concentration. All right, mole per dm cube, mole per 1 dm cube of the solution. It's not so simple if your volume is not 1, yeah, for example. So at the bottom you have mole per dm cube time mole per dm cube. So this looks slightly more complicated than the first example there, because then what you will get 1 over mole per dm cube, and you have to simplify it into mole minus 1 dm plus 3. Okay, that's the reciprocal of these units. All right, so moving on, example 3 is an algebraic expression kind of question. Okay, so it involves algebra. As you could see, the numerical value of Kc for reaction 1 is 2. So if that Kc is 2, they're asking what is the value for reaction 2. Okay, I hope you can see that here you are making x2y, you're making 2 of it. Here you are reacting the opposite way, which is going that way, and you have half of that equation. So how is it different? All right, so I guess it's important for us really to just write down the expression of Kc for the first reaction, which is x2y, concentration in square bracket, to the power of 2, because that's the balance equation there, is shown to the power of 2, divided by the concentration of x2 square, because there's a 2 in front of the x2, and the concentration of the y2 to the power of 1, so that's equal to 2. All right, how about reaction 2? So for reaction 2, on the right hand side, I have x2 to the power of 1, that's the concentration of x2, y2 to the power of half, and x2y to the power of 1. These are all just based on the equation given. The right hand side concentration raised to the power as appropriate from their balance equation in this particular reaction over the concentration of the reactant raised to the power of whatever the balance equation. Alright, so I need to think about how to relate this to this. Okay, I can imagine this being, first of all, I think it's easier if I just square them, because I could see there's a square and there's a power of 1. So what do I mean by that? If I square this, then this will become to the power of 1, then this will become square. But I'm using the sign equal here. So this is not equal to that. But I can make it equal by having a half. There's the square root. That means I take the square root of this, I will just get this back again, because square root of, I hope you've done this in maths. So that means you can get that back. It's just like, instead of concentration, if you have a squared over 1 over 2, you get a. I hope that's easier to see. All right. So your a basically is just the concentration in this expression. And here, this is 1. So when you have a to the power of 1 half, it's just back to a half. All right, so essentially that is now equal to that with the use of half. The reason why I choose this particular expression and not cube or whatever is because I can see the similarity. I want to express this in terms of this value, right? So I need to make it into a familiar form, just like that, so that you can see what is going on. All right, so what next? So should probably add one more page there. Okay, I'll move this down here. So there's Kc2, let's say. There's Kc1. Okay, so what else now? I see that they are upside down, meaning to say here the x2y square is on top, x2y concentration square is at the bottom. So this is also equal to 1 over Kc1. Because when you do 1 divided by x2y square over x2 square y square, what it means, okay, maybe it's easier if I use expression. I will show you what I mean. 1 divided by A over B is equal to 1 times B over A. That is something you would have done in primary school mathematics. We want to get the other way around. Therefore, we 1 divided by that. Then it will swap the order around. It will give us back that again. That's how I get the expression to be 1 over this whole expression there. Okay? And don't forget 1 over 2, because inside is equal to that, but the outside there's a square root to the power half. Do I know this value? Yes, of course I do. Look, there's the identity there, there's 2. So what this tells you really is, therefore, Kc2 is equal to 1 over 2 to the power half. You can simplify this further. To the power of half means square root, which you will have done in maths again. Square root of 1 is 1. Square root of 2 is just, well, root 2. Yeah? So this is the value for Kc2 because they give us the value of Kc1. At first glance, it looks like, oh, it's just the other way around. Some people will have put down negative, but the equilibrium constant is never negative. It's always between 0 and a number bigger than 0. It is never negative. Okay, just because you go the opposite way, it's not negative. It's actually the reciprocal. Okay, we need to say 1 over the 1 over the previous Kc value, and then of course the multiple matters as well. And it's not just half or square or whatever. It's actually to do with more than just half or double. It's to do with the power, because the number in front of the stoichiometric species there represents a stoichiometric quantity, and that's what we raise the power to. So this is a very good question on algebraic manipulation of Kc. Yeah. So moving on to question 4. So we are doing something more complicated now. So in the sense that when you have 1 mole of each of ethanol and ethanol acid, so you should have your equilibrium table drawn up nicely or written up nicely. When I say a table, I'm not going to draw a line or anything, but what I am going to do is I'm just going to outline to you how it happens. Mole at start, or sometimes you can say initial mole or whatever at the start. You start with 1 mole, you don't have a product, okay? Then your mole at equilibrium. You want the mole of ethyl ethanoate form. So let that be X. So what is X? X is the mole of ethyl ethanoate at equilibrium. If X is the mole of ethyl ethanoate at equilibrium, then we need to look at this equation and how we can manipulate it further. Alright? I'm going to add a page there because I think this one will take up quite a lot of space. You are given the Kc as 4.00, and that Kc is at 60 degrees Celsius, and this equilibrium is at 60 degrees Celsius, so we are okay. For as long as temperature doesn't change, Kc doesn't change. Alright? Temperature is the only thing that can change the value of Kc. So previously, you were asked to find the value of Kc, but here you're asked to find the concentration, or in this case the mole. Okay, they don't give you the volume, and that's the reason, even though we're supposed to be working in concentration. So let total volume equal to V, and you will see why it doesn't matter later on. Okay, I'll start by thinking about filling in this table. How do you do that? This is the balanced chemical equation. What does it mean? 1 mole reacts with 1 mole of that to form 1 mole of this and 1 mole of that. Okay, so in terms of mole ratio, the mole of water form, so you got to think about what is formed and what is reacted. So I would encourage people or students who are doing this to always think about and write down what is formed and what is reacted, specifically for equilibrium. It's very, very important not to get sidetracked by something you might not have thought of. Okay, sorry, not ester reacted, ester form. So they are going to be equal because it's just 1, right? The ratio is just 1. So the mole of water form is equal to the mole of the ester form. And how much of the ester do you form? You form X mole. Well, that's what you want to find, right? The number of mole of ethyl ethanoate, the ester, let it be X. So if I know that, which is X, I can work out the mole of water form, which is X. Therefore, that is X. So we are slowly filling in our table, yeah. What else? So the mole of this reacted, we can compare with the ester that's formed, yeah. So it was 1 to 1, right? Okay. So the mole of the ethanol is the reactant, so it's the reacted over the mole of ester formed. It was again 1 to 1. I could have done it straight away, but I would just want to show you 1 mole of this give you 1 mole of the ester. 1 mole of ethanol reacts to give you 1 mole of the ester. Alright, so therefore, how much of the ethanol reacts? Okay, this is the ethanol reacted. You need to be very careful. How much of it reacted will give you, however, how much is formed. Alright, you started with 1 mole. You started with 1 mole. How much of it has reacted? Reacted X mole. How did I know that? Well, I just shown you using the mole calculations, which I shown a lot in the calculation video on simple manipulation of mole ratio. You could always check it out if you want to. And then that would give you 1.00 minus X. Started with 1 mole, urea X mole, you get that. How do I know urea X mole? Mole ratio, okay? It's simple here because everything is 1 to 1, and you can see the mole of the acid reacted is equal to the mole of the ester formed as well, because it's 1 to 1, so it's still X. So you get that, you get 1 mole of it from 1 mole of this that react. You get X mole of this because X mole of this react, okay? So this is nice and simple. It's also reacted X mole. So therefore, you get 1 minus X. Ideally speaking, we should be thinking about volume. We should be thinking about volume. So if I have another line at the bottom there, which I will just very quickly show you. If I have another line, so there is concentration, because Kc is to do with concentration equilibrium, right? So it's the mole over the total volume, the mole over the total volume, the mole over the total volume, and the mole over the total volume. I'm given the value of Kc. Now I need to find X and what is V. I'm not even given V in the question. I've just assumed the total volume to be V. But they will cancel out nicely, simply because the Kc is going to be the concentration of the ester, the concentration of the water, the concentration of the acid, the carboxylic acid, the concentration of the alcohol. So this is esterification, which you will have done in O-level. Yeah, and you will revisit this in your A-level organic chemistry. So that is equal to 4.00. The power is all 1 because it was all 1 to 1 to 1 to 1. The ester and the water is on the right hand side. They appear on the top of the equation. From the table, you have X over V times X over V. At the bottom, you have 1 minus X over V. 1 minus X over V, that is equal to 4. You can immediately see, I hope, 1 over V square over 1 over V square is equal to 1. So the V will cancel out, yeah? So the V will cancel out. That's why the total volume doesn't need to be known in this question, alright? In other type of scenario, you might need the V total, but in this question, we should be working with concentration because Kc is to do with concentration, but you don't need to know total volume because they do cancel out. Alright, so what do I get? I get X squared over 1 minus X squared equal to 4. Start to use whole number because it's quite simple now. This is a quadratic equation, so you need to open up and expand the bracket. So it's 1 minus X times 1 minus X. So that is 1 minus X, and then at the they will give you minus X plus X squared. So it's 1 minus 2X plus X squared, yeah? So this is the kind of maths you can expect. It's not high level kind of mathematics, but you need to solve this quadratic equation. Do you need to solve this quadratic equation? That's what I'm thinking. Hang on. Okay, you can solve a quadratic equation, but I think there's an easier way to this, because we can automatically discount the fact that that you don't have a negative root. Because what is X? In mathematics, you can have positive and negative root, right, when you have a quadratic equation. but X is a quantity of mole. Okay, mole can never be negative here. It's always going to be greater than 0. And therefore, what I can do is, I can square root both sides. If I square root both sides, what it means is there is x over 1 minus x squared, that is 4. I square root both sides. That means I'm going to get x over 1 minus x is 2. You cancel out, or you omit negative 2 value, because x cannot be negative 2, yeah? As in, like, it wouldn't be negative. So what it actually gives you is that 2 minus 2x. So 3x equal to 2, x equal to 2 over 3. Does that make sense? X equal to 2 over 3? Well, when x equal to 2 over 3, 1 minus 2 over 3 is still 1 over 3. So 1 over 3 is still a positive value, okay? If there's 2 over 3, 2 over 3, they are greater than 0, it's still a positive value, so that one is all valid. There's the fraction, there's the exact value. Of course, you can convert it into decimal, then you get things like 0.667, and these are all given as 3 sig fig, okay? So if you are in theory paper, so I suppose you can show 0.6667 like that, which of course, you know, you can run it up to 0.667 to 3 significant figure, and there's no unit. There's no unit because, as you can see, mole per dnq times mole per dnq divided by mole per dnq times mole per dnq. Okay, so that's why there's no unit. However, I'll keep it as the exact answer if always possible, unless I'm specifically asked. I guess both are correct, really. Okay, so why is this question complicated? You see this quadratic equation and you already immediately think you have to do that, but we can omit one of the root because it will give you an answer for x which is not sensible. All right, what else is difficult? People assume that it's always just x or whatever here, but dependent on what has been formed resulted from what has reacted. If you know what you started with and you can work out how much you reacted with, therefore you can work out the molar equilibrium. That's what makes this kind of question complicated, yeah? Next question is even more complicated because we are no longer dealing with 1:1:1, okay? So I hope you can see what's going on here. Let's construct our equilibrium table, just a very imaginary equilibrium table. So you have the mole at start, or you can label it initial mole. You have 4 mole of NO2. The volume is 1 dm cube again. I think they try to make life easy, but do not assume it's always 1 dm cube, so read the question. And what else? You have the mole at equilibrium. Equilibrium mixture contains 0.8 mole of oxygen. Alright, so now we need to think about what has reacted and what has formed. The O2, initially you will have 0 and 0. That's what you started with. But some of it dissociates and give you that. So the mole of O2 formed, because O2 is a product, relative to the mole of the NO2 reacted. The O2 is formed from NO2 that reacted is 1:2. 1 mole of O2 is formed from 2 mole of NO2. Okay, I'm running out of space there, but what I can do is I'm gonna move the 1/2 now, and then on the right hand side I will properly put in the value of whatever is the actual thing. Okay, so 0.8 mole of oxygen is actually formed. Top bit is for oxygen. 0.8 mole of oxygen is actually formed. Okay, therefore how much is the NO2 that reacted? So therefore the mole of NO2 reacted is, I can move the NO2 reacted up there. I will get 2 times 0.8, which is 1.6 mole. So 1.6 mole reacts, 1.6 mole reacted. Therefore, since you started with 4 and you reacted 1.6 mole, you are going to end up with 2.4 mole left at equilibrium. Start with 4 mole, you reacted 1.6 mole because mole ratio. Okay, what has reacted and what has formed. Alright, so I hope the next part is even easier because I could imagine that the mole of the NO, the mole of the NO that is formed relative to the mole of the O2 that is formed. So I'm talking about both of these being product. So both of these are being formed. It is still 1:2. 1 O2 is formed alongside 2 mole of NO. So therefore, how many mole of NO is actually formed? Okay, I should put in the value just like I did before. Okay, so usually I will put in the value on the side there, but I'm running out of space there. I hope you know what I'm doing. The 1/2 comes from the balance equation. Okay, both of these are product, both of these are formed. Whereas I want the actual mole of NO form, I know the actual mole of O2 form, which was 0.8. I was told you have 0.8 mole of oxygen equilibrium. Started from nothing, you have 0.8, that means you form 0.8 mole of oxygen. So the mole of NO form is, have I done something wrong? Let me see. Yep, I've done something wrong. The mole of NO form is 2:1. Okay, so the mole of NO form is 2:1 because from the equation it's 2 mole of NO is to 1 mole of O2. Okay, you see, it really does not matter as long as you label what you have and you follow through the fractions and you will be alright. I thought I had the same fraction, but I didn't. Okay, so you gotta be careful of what you write. Yeah, so that is going to be 0.8 times 2, so it's 1.6 mole. You started from 0 mole of NO. Now you have formed 1.6 mole of NO. Okay, form 1.6 mole. Therefore, started from nothing. Now you form 1.6 mole. You have you have 1.6 mole now. Okay, so that's the difference between what has reacted and what has formed. So now we have a volume because we need the concentration at equilibrium, but we know the volume was just 1 dm cube. So the mole divided by 1 dm cube is going to be itself. I'm just doing something extra to show you that we have concentration, which is in mole per dm cube. Mole per dm cube because now we need Kc. We write the expression of NO concentration in square bracket. We needed a square because there's 2 in front of the NO in the balance equation. Same like we have 1 in front of the O2 in the balance equation here. Okay, here we also have 2 in front of the balance equation, so we need 2. Now these are the concentration equilibrium. Each one of them represent the concentration equilibrium. So the Kc for this reaction would just be 1.6, which is the concentration of NO at equilibrium, times by 0.8 to the power of 1, and then 2.4 square. Put that into your calculator. That gave me 0.356. I guess the most this data give me is really just 1 decimal place or 1 significant figure. By right, I should really probably just round it up to 1 decimal place or 1 significant figure. Okay, so that's the end of this short video. Well, not really short, but that's the end of this first video of the 2-parter series on calculations of Kc. So do watch the second video for more examples and variation on how they can ask you questions on Kc. If you haven't subscribed to the channel, please do. If you like my teaching style and explanation, please share with your friends and colleagues as well. Thank you for watching.